Imagine you're sitting in a garden when, out of nowhere, a wasp stings your arm. The pain is immediate. You quickly pull out your phone and search the internet for what to do. The first few websites, the top YouTube videos, and even many old science textbooks all give the same advice. Wasp venom is alkaline. Apply vinegar to neutralize it. So you rush into the kitchen, grab a bottle of vinegar, and pour it onto the fresh sting. Instead of feeling relief, the burning becomes even more intense. It feels as though you've poured acid onto an open wound. You begin to wonder, if vinegar is supposed to neutralize alkaline venom, why did the pain get even worse? The truth is that you've fallen victim to a myth that has been repeated for generations. Today, we're going to put that myth to the test. We'll dissect a real wasp, extract its pure venom, and discover what the science actually says. Let's begin. According to biological anatomy, a wasp's body is divided into three main regions: the head, the thorax, where the legs and wings are attached, and the abdomen, which forms the rear section of the body. Right now, I'm working on the very end of the abdomen, where the stinger is located. This terminal section is known as the gaster, or the terminal abdominal segment. By placing the wasp on a watch glass and carefully separating the gaster with a surgical blade, I'm performing a microdissection, the process of isolating tiny anatomical structures for scientific examination. As I gently pull the gaster apart, you can see an entire structure emerging from inside. This is called the stinging apparatus. Attached to it are two extremely fine tubes known as the venom glands. These glands produce the venom and deliver it into a small transparent sac called the venom reservoir, or venom sac. I carefully removed the surrounding tissues and isolated the venom reservoir so I could obtain a sample of pure, uncontaminated venom. However, there's one major challenge. A single wasp contains an incredibly small amount of venom, far less than a single microliter. If I were to rupture the venom sac directly onto a dry watch glass, the venom would spread into a thin film, dry almost instantly, and there wouldn't be enough liquid to properly wet the pH paper. To solve this problem, I've added a single drop of distilled water. In chemistry, this process is called aqueous dilution. Since distilled water is essentially neutral, it increases the sample volume without significantly affecting the pH that we're trying to measure. Now, in the final step, I'll gently rupture the venom sac and release its contents into the droplet. Next, we'll immerse a strip of pH paper into the diluted venom sample. As you can see, the color of the pH paper doesn't change at all. It remains yellow, corresponding to a pH between approximately 6.0 and 6.8. According to biochemists, this indicates that wasp venom is physiologically close to neutral. In other words, its pH is roughly similar to that of many of the body's own fluids rather than being strongly alkaline. This experiment challenges the long-standing claim that wasp venom is alkaline. If the venom were truly alkaline, the pH paper would have changed to a deep blue or purple color.